All right, guys, I'm going to pick up with partial sums from yesterday. So remember the sequence yesterday was just a list of numbers, right? Just a list. There could be a pattern to them. There doesn't have to be a pattern. When there is a pattern, we like to try to analyze it and describe what that pattern is. Algebraically, it's kind of a rule. But, you know, sometimes sequences, just because by definition they're just a list, maybe there isn't a pattern to them, okay? And maybe we can't come up with a real nice, clean algebraic expression. So those are things I think you should keep in mind as we work through this stuff and as you encounter them, specifically in a math class. A lot of times, though, I'm doing like a textbook or web assigned homework. Obviously, they're going to create and give you lists that do have kind of a pattern to them, right? But just in general, that's not necessary. If we want to start looking at things called partial sums, okay, we can start adding our values in our list together, okay? So a partial sum says take the first however many terms and just sum them, okay? So if I want the first partial sum obviously is just the first term, okay? Don't have anything to add together with it. But if I want the second partial sum, okay, so we see S sub 2 there. All that means is you take your first term of your list, add it to your second term of your list. So I want S sub 3, or my third partial sum. I take my first term plus my second term plus my third term, okay? I can do that for how many terms I want to add together throughout my list, okay? If I want to add the nth terms, it's first one, second one, third one, fourth one, fifth one, all the way up to however many n was. Is it okay? That's called partial sums. Now, just a little notation that I think is important. Obviously, we use the S for sum, okay? But when you get to, and even in this class here in a little bit, we'll talk about this, where that leads us to, just a second. All right, so S for sum, that's going to lead us to this. You guys remember what that is from last year? That's sigma, okay? It's the Greek capital letter for S for their sigma. It's, lowercase sigma looks like this. But that's capital sigma, and what does it stand for? Sum, okay, right? Eventually, so when we talk about sigma, in this class, you'll use it a lot in calculus. It's kind of the predecessor to what we call integrals in calculus. Sigma notation is going to allow us to count a finite number of things or add a finite number of things. So if I want to add up 10 objects, 12 objects, maybe 100 objects out of my list, that's what sigma notation does, okay? Calculus works on the idea, it says, okay, what if your list is infinite, okay? And you want to add up all of the things that are in that list, okay? We don't use that notation anymore. We use this notation. And it's a really skinny looking kind of S with these little two hooks on the top and the bottom. And that's called an integral. We use it's called integral notation. Now, with integral notation, what you will learn is that you can still deal with a finite number of things, but overall the purpose is to eventually get to the idea that we are interested in an infinite number of objects to add together. Just to give you kind of a brief kind of understanding of why we're doing this and why we're talking about these summations, is that in these partial sums, in calculus the goal is to take some curve. Maybe that's the curve. And from that point there, A, to that point B, we're interested in finding the area under that curve and above the x-axis. So that little block of area is what we're interested in, okay? So what we do initially, we use something called Riemann sums, is that we block that thing off into rectangles, okay? So, and there's several different types of Riemann sums. We can do rectangles where they're called left shoulder points, or some called right shoulder points and that kind of stuff. But basically means chop this thing up into rectangles. So this would be left shoulder because the left shoulders of my rectangles are on the curve. But I do that and maybe that's my rectangles, okay? Now, are some of those rectangles like overhanging? Yeah, okay, so that would be an approximation, all right, of the area underneath. So what we do is, like I say, well, if that's, I don't know how many that is, 7 or 8 rectangles, my approximation would get better and the overhang would get better or get minimalized if I used 20 rectangles instead of 7 or 8, right? Or if I use 50. But what would be the best thing to do? Use an infinite number of rectangles, okay? So the summation idea of 8 or 9 or 10, that sigma notation, will be what kind of leads us into eventually saying, okay, well, what about infinite now? What infinite number of triangles? And the whole thing that kind of goes along with that is that the more rectangles. The more rectangles that I put in there, the more I've got geometry on my brain. The more rectangles I put in there, the narrower and narrower they get, right? Okay. So you'll talk about that concept later on in calculus, but that narrowing of the width of our rectangles, we want that value to become closer and closer to 0. Okay, we want it to approach 0, because then you've got very, 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 very negligible overhang in your rectangles, and we have a very, 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 very good, accurate area. Does that kind of make sense? So this is getting you're going to see all this stuff again next year. And part of calculus is dealing with certain types of sequences and series and how you can use them to target some of our calculus concepts. That's the purpose of them. And so the idea is if you know that you're going on to calculus next year, the stuff that we talk about right now is going to be reiterated. Okay, you're going to talk it. So if we just skim the surface now, you're going to talk about it again next year in a lot more detail. But if I want to do partial sum, so this formula here, a sub n equals 1 over 2 to the n. Okay, so we've seen this one where you're basically just taking 1 divided by your powers of 2, right? So you get 1/2, you get 1/4, 1/8, you get 1/16, 1/32, 1/64, and so forth. Okay? Well, if I want to find the first partial sum, well, that's just equivalent to the first term in my list. I don't have anything to add together, it's just that first object, so 1/2. Okay? If I want the second partial sum, it's going to look like that. Okay, I take the first term, which was 1/2 in my list, add it to my second term, which was 1/4 in my list, right? Common denominator, add them together, I get 3/4. I want S sub 3, that's the first term, 1/2, second term, 1/4, third term, 1/8, add them together, 7/8. And keep doing that however many partial sums they're asking for. Is that something we can do? Seems pretty easy, right? Okay. Now what they want to do sometimes is ask you, okay, if you think about your partial sums, so S1, comma S2, comma S3, comma S4, that's a sequence, isn't it? If I go S1, that was 1/2, S2 was 3/4, S3 is 7/8, and S4 is 15/16. So I use my original 1 over 2 to the n to come up with these partial sums. If I list my partial sums in order, I have a sequence. Is that okay? Can we figure out a rule for that sequence? Look at your denominators. 2, 2 squared, 2 cubed, 2 to the 4th, right? So your denominators are still 2 to the n. Okay? How do your numerators relate to your denominators? They're 1 less. So I get 2 to the n minus 1 over 2 to the n. Does that make sense? Okay? Now, something that's just an interesting thing, and this is why sequences and series are investigated, the relationships are interesting. It's an entire branch of mathematics. If I plot my 1 over 2n list or sequence against my summation sequence, look how they relate to one another. Okay? They're parabolic, aren't they? Opening to the right. But that's a pretty interesting feature, pretty interesting relationship between those two lists of values. And the fact that one of those lists come from summating the other ones. Not something we'll do a whole lot of. Ask you to come up with a rule for your summations, but they will ask you, okay, find the first sum, find the second one, find the third one, find the fourth one, and kind of usually leave it at that at this stage of math. When we talk about sequences, there's two types of them. There are finite ones. What's finite mean? So it ends, yes. Okay, so you can attach a numerical value to each one. You can count how many things you have, right? Okay. So I look out in the courtyard. There are a lot of blades of grass out there, right? But they're finite. I can go out there and pluck every one of them out and count them, right? It might take me the rest of my life to do that, but you can do it, okay? An infinite sequence means it keeps going on and on and on and on. You cannot collectively tell me how many things you have in that list. Does that make sense? So finite and infinite sequences are just terms that we might use periodically through some of this investigation of sequences. Another term or series of terms that we're going to use is the word convergent and divergent. Okay? If I'm walking down the hallway and me and Devin Grigsby are getting really close to one another and neither of us know which way to move. I don't know, move left, right. He moves left, I move right, and we converge on each other, right? We hit each other. Okay? So when you converge, you're going to run into something. Does that make sense? Okay? So when my sequence converges, it means it's running into something. It's running into some value, some predefined value. Does that make sense? So convergent sequences are getting closer and closer to some known number, known real number. Okay? So, think about 1 over 2n. 1 over 2n, or 2 to the n, sorry. It could be 2n as well. It doesn't really matter. Just 1 over 2n converges faster. What is this converging to? Yeah, okay. Eventually, because that denominator is changing, getting bigger and bigger and bigger, right? So if we were to graph those, you would see that you're converging. Your y values are getting closer and closer to 0 as you move on to the right, okay? Now, there are sequences that are divergent, okay? So I go, let's just go 1, 2, 3, 4, 5. It's a pretty common sequence, right? Just your natural numbers. Is it getting to one particular predefined value? No. It's diverging off to infinity, right? Okay. If I go 1, negative 1, 1, negative 1, 1, negative 1. Okay. That is just the, what was that? Negative 1 to the nth. The opposite. Okay. So that's that sequence, right? That's the rule for that sequence. Is that narrowing in on one particular value? No, it's just bouncing back and forth between negative 1 and 1, right? Okay. So the further I go out my sequence, I'm not going to zero in on one particular value. So that's said to be divergent. Okay. When we start talking about arithmetic and geometric sequences, we are going to be very, very interested in whether those sequences converge or diverge. Okay. And we'll have some tools, some algebraic tools that help us make that decision. But again, sequences are just lists of numbers. So some of them, if I just put a haphazard random sequence up there, it's probably not going to converge to something. Does that make sense? Okay. Usually there's got to be some type of pattern that we're seeing so we can make that argument of convergence. Here's just showing you 1 over n. Okay. So 1 over 2 to the n, 1 over 3 to the n, all of them would look very similar to this. As we move out to the right, we're graphing these terms. in the XY plane, you start to see that the Y values are getting smaller and smaller and smaller, right? But because of how we understand that, the denominator is always going to get bigger and bigger, but the top has to stay 1. You're getting closer and closer, so you never get to 0, but you get closer and closer to it, right? You kind of get to that asymptote, okay? Now, understand that when we graph those, because I don't have, in my list, I don't have a 1.5 position, right? I don't have a 1.111 position. So we don't connect those dots, okay? It's just a scatter plot for us, essentially. But it's still a function, still passes the vertical line test. So all that stuff okay? Sequences so far? Just basic terminology and understanding what they are. This one, n squared. So really any power function, n squared, n cubed, n to the 4th, n to the 5th, they are going to be divergent because as I start plugging in values and squaring them, you know, I'm getting larger and larger and larger and larger values in those positions, right? So you're not seeing it zeroing in on one object, one predefined real number. So that's said to be divergent. Okay. I'm not going to do a whole lot right now with whether a series or sequence is convergent or divergent, but it's important vocabulary for when we get to section 13.2 and 13.3. Okay, so talking about arithmetic and geometrics, which we'll pick up on Monday and Tuesday. Sigma notation. So this is going to be just a little bit of work, a little bit of analysis of how we can sum things using sigma notation. Okay. Again, we already talked about that symbol being the Greek letter for sigma. It's a capital letter. It's RS, which we use S for sum. So there's that link there. Now, the A of K or A sub K, that is referred to as your rule. Okay, or, you know, so it's going to be your function essentially. It's going to be, you know, maybe it's 1 over 2 to the n, or maybe it's 1 over n, or maybe it's 2 squared, or something like that. Okay, or you know, n squared, whatever your algebraic rule is that A sub K. Okay, whatever's producing your objects in your list, right? Okay, the K equals 1 on the bottom. Okay, is what we refer to as our index. Okay, meaning that that's going to tell you where you start in your list and how you move in or move throughout your list. Okay. A lot of times, if we have, it's like a counting device. It's a device that allows me to move from my first object in my list to my second object to my third object. Whenever that happens in mathematics, you have something that does that for you. It's called an index. Okay. And then that number on top, that n, is going to be our upper bound for our sum. It's going to be our last term in our list that we're adding together. Okay. We really, really like it when K is 1. We start off with 1, but it doesn't have to. We can start off with the 3rd term, the 4th term, the 5th term, whatever. The only thing we have to pay attention to is that K term on the bottom, that value has to be less than n. Does that make sense? Okay, I can't start at my 3rd term, but n only goes to 2. So there's some examples of this and try to give you a kind of an appreciation for some rules here that we're going to see that allow us to do summations a little bit faster. Okay. So you see again that this is calling the letter K the index. And basically that number on top, in this case it's 5, is going to tell us when we stop. Okay. So if I want to find, basically if I read that first part there, it says find the sum of the sequence K squared of the first 5 terms. Let's come up with the partial sum, the 5th partial sum of K squared. Is that all right, everybody? Okay. We're going to do this by hand. We'll do this the long way, and then I'll hopefully go back. We'll have some time to show you some properties that allow you to shorten this process. But all this is saying is, when you write your list, so I'm going to sum these together. I'm going to sum 5 things together. So this one is when K is 1. This one is going to be when K is 2. This one's going to be K3, K4, K5. Okay? And that information is gained from that object in that object. Does that make sense? Okay, so When k is 1, I'm left here in this object as 1 squared, right? When k is 2, this one would be 2 squared. So we're just taking our k value and squaring it, right? This would be 3 squared. This would be 4 squared. That would be 5 squared. And now the thing that kind of stinks about these, without our rules that I'm going to show you here in a little bit, you actually got to go in and do the simplification and the evaluation, essentially. Okay, so that's going to be 1 plus 4, there's 5, right? Plus 9, give me 14. Plus 16 would give me 30, right? Plus then 25. That summation is 55. And you could do that then with however many terms that you wanted to. Okay? If I just wanted to start with, you know, if I do this second one here, I think the next slide maybe does the second one. If I do that second one, okay, I don't have to start at 1. Okay? Now, some of the properties I tell you in a little bit, you will have to start at 1. But this is saying find the third term, the fourth term, and the fifth term, and add those together. So basically what's happening here is when I want to find the sum of j equals 3 to 5, okay, oh, 1, 2, 3, 4. I got 5 objects there, but j equaling 3 says you are not going to pay attention to that one and that one. They're not going to be part of our sums. Does that make sense? So it's only the third, the fourth, and the fifth things. So if j is obviously 3, I'm going to get 1/3. If j is 4, I get 1/4. If j is 5, I get 1/5. And now you can sum those together, and you're seeing here, once you get common denominators, all that kind of stuff, you get 47/60. Okay? Does that make sense to everybody? Okay? I want to look at that C one, and I want to do a couple different things with this C one, because I think it's going to be beneficial later on if you got to do just some problem solving skills. So let me just kind of clean this up real quick. All right, so obviously we do what that initial list said, okay, in the fact that you start at 5, you're going to go to 6, go to 7, 8, 9, and then 10, right? Eventually, I'm going to be asked of this, but I don't want to really use that process. I don't want to just write all 6 of those terms down and add them up, okay? Would this make sense, okay? If I've got, so basically I'm missing 1 plus 2 plus 3 plus 4 in that list, right? Would you guys agree that if I take I equaling 1 to 10, okay, so that list is going to look like 1 plus 2 plus 3 plus 4 plus 5, 6, 7, 8, 9 to 10. And I subtract from that. I equaling 1 to 4 would be minus 1 plus 2 plus 3 plus 4. Does that make sense? If I did that, okay, so this minus 1 here would cancel out with that one there, right? This minus 2 would cancel out that positive 2. Minus 3 with positive 3. Minus 4 with positive 4. And what all are you left with? 5 plus 6 plus 7 plus 8 plus 9 plus 10, right? Is that the same thing as I equals 5 to 10? I wasn't putting I on these, but does that kind of make sense? So if you're asked to start somewhere in the middle of a list, in the middle of a sequence, maybe at 5, you don't necessarily have to just start it, but you could find 1 to 10 and remove from it 1 to 4, and that's going to give you 5 to 10. Does that make sense? Okay, so you can that's really never taught or explained in many pre-calculus textbooks, but it's a problem-solving skill that they assume that you have already developed, and you can work through that on your own. So I want you to see that because it might be something we use, and hopefully maybe we have time here in a little bit to give you a specific example of that with some of the rules that we're going to deal with. Okay? The last one was I equals 1. I'm not going to, we'll do this. 6, and then this was 2. Okay? So there's no variable part in this rule, right? Okay? So my first term is going to be what? 2. What's my second term going to be? So this I goes to 2, and it just tells me that you then put your rule with that I here. It's got to be 2 again, doesn't it? Does that make sense? Third term, so I get to the third term, so this would be a 3. My rule, 2. Fourth term, 2. Fifth term, 2. Sixth term, 2, right? What's that sum? 12. How do I get that? Yeah, that's repetitive addition, right? Repetitive addition is simply defined as multiplication. 6 times 2 would give me that 12, right? Okay. Here's the thing that I was, in that last question, let's say I started with, or something similar to that last question. Instead of starting at I equals 1, let's say I starts at 4. Okay. I is starting at 4. Let's go up to 30. Okay. Of just 5. Okay. Do you want to write out all of those terms? No. So I think the best thing to understand here is that should equate to the same thing as I starting at 1 going to 30 of 5, right? Minus I starting at 1 going to what? If I go to 4, I'm going to kick out that fourth. I'm going to kick out, basically subtract away this first object here, right? So I'm always going to go to 1 less than what that was. 5, right? And now using this kind of process here to find that, I have 30 times 5, which would be 150, right? And I've got 3 times 5, which would be 15. That can be 135. Okay, so if I wrote down the 4th term, the 5th term, the 6th term, all the way out to the 30th term, and add those all up, I'm going to get 135. Okay, that's the most simplistic way of doing it because really it's really easy to find those sums of 5 to 30 and 5 to 3, right? But that is a simplistic way of showing what we would do in the next couple examples if we were not starting at 1 in our next couple examples. So this rule here, if I call, obviously, I equals 1, let's call this n, and this just a constant, okay? Well, what you're seeing there is that constant is going to be written out n times, isn't it? Okay? So that is going to be n times. Well, if I have an object written out n times, okay, that's repetitive addition, right? Repetitive addition is taking that object times how many of that object you have. So when I have this summation, I can always rewrite it as C times M, so I can get there quicker. Does that make sense? Okay, so I don't have to write them all out. And you're going to see a lot of rules that are like that. So that rule here, so these are the following properties that I want to talk about. That's the last one. Actually, no, that's not the last one. That's actually a property on this slide here. Let's talk about those 3 first, though. Okay? Because they're very useful, they're very similar. Here the idea is if I have a sum a sum in my rule. So let's say that I have, let's say we're using I. So I starts at 1, and we're going to n of, let's just say, I plus 3. Okay? What this rule here is saying, what rule number 1 is saying, or property number 1 is saying, is that that is equivalent to saying I equals 1 to n of just I plus I equaling 1 to n of just 3. Okay? We can break that summation up into 2 individual sums. Does that make sense? Why is that useful? Because now, instead of having to say, okay, well, if I is 1, okay, then we'd have 4. If I was 2, we'd have 5. If I was 3, we'd have 6. And we write the list that way, right? And we can then start adding all those up. Well, this here, isn't that really going to just be 3 in there? That makes sense to everybody? So breaking this up allows me to see how much that thing there, essentially how much that 3 right there contributes to my entire sum. It contributes 3 into my entire sum. I'm going to show you a rule here in a moment that allows you to find I, from I equals 1 to n, that sum, very quickly. But all that is your 1 plus 2 plus 3 plus 4 plus 5 plus 6. It's the summation of your natural numbers, right? Okay? But breaking that thing up like that is going to be very useful. And we could do some very specific examples that shows you, yeah, that makes sense. I can do that. I'm always going to get the sum the same way. So if I did, let's do one of these. If I go this side here, so I've got 1, 2, 3. So the fourth term would be, 7. Fifth term would be 8. If I add those up, okay, just going out to 5 terms, so I get 9, 15, I think it'll be 22, 30, right? Okay. Well, if I do this here, so that list there is going to be 5 terms. It'd be 1 plus 2 plus 3 plus 4 plus 5, right? If I look at that, that's going to be, so there's 6, 10, 15, right? And now look at this. So this here would be 3 plus 3 plus 3 plus 3 plus 3. What's that give me? 15, right? So this was the sum of I. This was the sum of 3. If you add those two things together, does it give you the same thing as that? Does that make sense? So this 30 came from that side. This 30 came from that side. They equate, right? So we can do that. We can break them apart into individual sums and then add those individual sums together. You can do the same thing with subtraction. Just be careful with subtraction. Order matters in subtraction, right? Okay. And then the last one there is saying if I've got something like 2 times I, so I is 1, and we go to n, well, that's going to look like 2 plus, then it'd be 2 times 2, right? Okay, so 2 times, I'll write it this way, 2 times 2, plus then it'd be 2 times 3, plus then it would be 2 times 4, right? Does that make sense to everybody? Well, what does each one of those have in common? It'd be a 2, right? So I can bring that out, and I'd be left with 1 plus 2 plus 3 plus 4 in there. Well, what is that? That is just the sum of I, isn't it? So 2 times the sum of I, you see then that what we can do is if I have a coefficient here of 2, or anything, in this case they're calling it C, you can do this process. You'll always be able to factor that out of every term, so write it out front instead. Does that make sense? Okay, so those 3 properties are very useful, and those are a little short. If we're doing a proof, we want to do a little bit more kind of organization of our ideas and stuff like that, and we'll be a little bit more specific, but you can start to see why these properties maybe exist and why they work. Why is that beneficial? They're going to ask us to use n values that get very, very, very large. Okay? If n was like 1,000, do you want to write 1,000 terms out? No. Okay? So some of these properties will allow us to kind of consolidate our work, make our work a little bit simpler. Okay? We also have these summation rules, summation laws, and I'll prove one of them with you, but the other ones are proved the exact same way, and then maybe not the exact same way, but a similar fashion, using similar types of proofs. They're called proofs by induction. That first one we've already seen. That first one just says if I'm starting at I equals 1, going to n of just some constant, then I'm going to have that constant being added together over and over and over again, right? So it's going to be repeated addition, which is just multiplication. So I take c times however many c's I have there, and that number that I'm going to have is equivalent to n. So I take c times n to get my sum there. Does that make sense? Okay. Now we'll look at that middle one, or not middle, that second one. Okay. And that's just your integers, correct? Or not your integers, your positive integers, your natural numbers. Okay. I want to prove this just real quick with you. If I have I equaling 1 going up to n of I, okay, would you guys agree that that sum, okay, of n objects, I'm going to write it this way, the sum of n objects, would you agree that that is going to look like 1 plus 2 plus 3 plus 4 plus all the way up to n, just like this says, right? Does that make sense? Okay. I want to do something a little bit different. Okay, think about this. If I gave you this list, 1 plus 2 plus 3 plus 4, and I asked you to add those together, 1 plus 2 plus 3 plus 4, what do you get? You get 10. Okay? So when you add it going that way, you get 10. When you add it going that way, 4 plus 3 plus 2 plus 1, what do you get? 10. Because the commutative property of addition works, right? Okay? So here's my question. If this is my sequence, or sorry, when we add them together, we start talking about them as being series. But if this is my summation going left to right, wouldn't my summation going right to left start with n? Does that make sense? And what would be the object before that then? It'd be n minus 1. So I'm going to add to this n minus 1. What would be the object before that? N minus 1 minus 1, which would be n minus 2, correct? And the one before that? N minus 3, and I can keep doing that, right? Eventually, am I going to get down to 2 and 1? Does that make sense? So eventually my last term is going to be 1. All right, so let me ask you this. Those two lists are the same thing, right? Let's add these lists together. First object to first object, second object to second object, third object to third object, okay? So if I added these two things together, you'd get what? 2SN. And that should make sense. If I want to add this list to that list, I should have 2 of whatever one of these lists was, right? Okay? So let's do this real quick. Let's go and look at the first object. So the first objects were 1 and n, right? What are you going to write down if you add those together? 1 plus n, right? I'm going to write it this way. I'll go n plus 1. Now look at that object and that one. Add those together. What's 2 plus n minus 1? N plus 1 again. Okay? Now, add that one with that one. What do you get? Simplifies n plus 1, right? What about that one and that one? N plus 1. So you start, and this is what induction is. Induction is seeing a pattern, okay? Because there's going to be some, when we got these ellipses, there's going to be a 5 and an n minus 4. There's going to be a 6 and an n minus 5, right? Okay? But the pattern is the same. Okay? So we can imply that the pattern is the same. And when I get to the last one, and the last one, what am I going to get? n plus 1. Okay? Now, how many objects were in that list? N objects. How many objects were in that list? N. So how many are going to be in this list? N. So right there, those n plus 1s, I want to have n of them, right? Well, going back up to this object, this idea up here, we have the same thing being added over and over and over again. Isn't it that object times how many times I have it? So shouldn't that equal 2 s sub n? But if I just want the sum of n objects, what do I have to divide both sides by? And that gives you that rule right there. Okay, so that's the proof of that. But what is that? Why do we have that? What is the use of that? Well, what happens when n is 1,000? Do you want to write out 1 plus 2 plus 3 plus 4 plus 5 plus 6 all the way up to 1,000 and then go back and add those? If you've ever counted to 1,000, it takes you some time, right? Okay. So if I want to find I from 1 to n equaling 1,000, we write that a little bit better. 1,000. All I have to do of I, all I have to do is write that as 1,000 times 1,001 all over 2. And I can grab my calculator, I can calculate that, and I've got the first 1,000 natural numbers added together. Does that make sense? Okay. Now, let's say that if I didn't start at 1, let's say I was using this and I was interested in, you know, the sum of I starting at 3 and going to, let's just say 100 of just I. Well, isn't that the same thing as I starting at 1 going to 100 of I? Remove from it the first 2 objects of that list. So the first 2 objects of that list would be I starting at 1 going to 2 of I. Does that make sense? Now that would be easy, but let's say we started at 30 instead. So then this would be, what, 29? And that would be a little bit, so if I wanted to add 30, 31, 32, 33, 34, all the way up to 100, see what that sum is, this would be the way that we could do that. And now I would take that and use that formula with the n being 100, and then I would use that with n being 29. Does that make sense? Okay. So these other rules are very similar. Okay. If I have I squared, this is a way of finding that sum of n objects. If I is cubed, that's a way of finding those n objects. If you did a quick Google search, you're going to find a list that can be very long. Okay, you go I the 4th, I the 5th, I the 6th, I the 7th. All those things exist. Okay, and there's rules for them, and they're all generated very similarly. But usually in calculus, you're going to only use maybe those 4. Maybe you go I the 4th and you learn that one. But let's talk about, you know, a benefit of this. Okay, so if I was going to be targeting that summation right there. Okay, you have 2 options. You can say, okay, well, if I equals 1, the first object would be 2 times 1 squared minus 3. And then when I is 2, we can go 2 times 2 squared minus 3. And then when I is 3, it'd be 2 times 3 squared minus 3. And I can do that 14 times, right? Is that going to be a pain in the butt? Yes. So let's do this. We can break this up. We can say, well, that is, and it's all going to, they're all going to have the same I starting off with, and the same 14. So a lot of times I forget to write those in. But can I do this? Can I break it up as a difference? Does that make sense, everybody? Can I take that 2 out in front? Does that make sense? Okay. And now if I can do that, again, this being I equals 1, this being 14, I equals 1, 14, okay? I squared, and initially you're going to have to probably have these rules next to you. Use them enough, you'll learn them. memorize them. But this object there is going to be that. Does that make sense? So we're coming to the side. I'm going to say, okay, n is 14. 14 plus 1 is 15. 14 times 2 is 28, plus 1 is 29. And I'll divide by 6. So that is just the sum of I squared. Does that make sense? From 1 to 14? Isn't there a 2 out in front of that? The 2 out in front would be this 2 here, correct? And then we'll subtract from it. Okay, this rule here is this first rule where I've got a constant here, right? So isn't it just 3 times 14? Okay. So we can evaluate that. You could grab your calculator, even if you can, maybe you don't need your calculator. You can 14 times 15 times 29 divided by 3. The 2 and the 6 we could cancel, right? And subtract from that, what, 42? And you should be able to find that sum. You're probably still, if you were going through that kind of direct way of substituting I into 2I squared minus 3, you're probably either still writing down all 14 of those objects, okay, or still going through and say, okay, what is 1 squared, what is 2 squared, what is 3 squared, that kind of thing, and simplifying them, all right, where those rules allow for that efficiency to happen much faster. And if you don't think that's more efficient, okay, change that 14 to 1400, okay, and then you start to see, yeah, there's a benefit to this, okay. We're going to jump into arithmetic and geometric sequences tomorrow. There's not a whole lot, guys, and there's nothing on the final, and I'm going to kind of do the same thing with the test next week. There's not going to be a whole lot of summation stuff with the sigma notation on those unless they're dealing with arithmetic and geometric sequences and the information we learned there. But I wanted to introduce that to you so that when you get to the calculus, maybe I remember doing something similar to this, okay? And you can say, I've already got a little bit of a footing with this, understand a little bit, and it makes then the calculus something you can focus on and not so much the algebra, right? Okay. So next week, Monday, Tuesday, Wednesday, hopefully finish up the sequence series stuff and then test on Thursday. And then that week we come back, we'll finish everything up and have our final.